Guys, you have seen the assumptions, right? By the way, what are these assumptions all about? Why are they assuming? Who knows? Why do we have these assumptions? Nobody knows? Really? Yes, not why we have assumptions in general. Why do we have these 10, 11 assumptions you have seen in this course?
Make it practical.
Practical easy? Are you sure?
Those assumptions are based on Gauss-Markov theorem.
What is the theorem saying?
To have the best, the blue, it's based on the blue, best linear estimated unbiased.
What is blue? What? You said to have blue. So which thing is blue?
Because it has two assumptions. You know your application is right.
Okay, I'll explain to save time. What are we doing in this course, econometrics? We are trying to do some kind of estimations, right? You collect data and you are trying to estimate relationships. You know, regression is relationship. I told you correlation, regression, causality, they are all relationships. But we are doing regression, right? So we are trying to find relationship between variables. But in order to quantify this relationship, in order to estimate this relationship, we have different methods. For instance, we have ordinary least squares. We also have a method called maximum.
The screen, will show the screen.
I didn't share my screen?
No, on the recording.
Just show you.
Oh, that's right. How did you take note of that? Okay, are you online?
I think
So all the time you check?
You never see that it's always have done in the past.
That's being smart. That's being smart, you know. Because I forgot actually. That's good. Okay, guys. So if we are trying to estimate the relationship, there are many methods to estimate. I will just mention two, but don't think there are only two. There are many. Like we have maximum likelihood. I'm mentioning just two because I want to explain something. So there are many methods we can estimate this relationship, but these are two methods. Now, generally, typically we use ordinary least squares, right? Why do we use ordinary least squares? We use ordinary least squares because they are the best. But it is the best. But why is it the best? It is the best only if these conditions are satisfied. That's why we have a certain theorem known as two guys, what's this? Gauss and Markov. They created a theorem known as the Gauss-Markov theorem. What is this Gauss-Markov theorem telling us? It's telling us that if these assumptions hold, if these assumptions are valid, then ordinary least squares technique is the best technique to use in doing this estimation. What do we mean by best? It means that the ordinary least squares estimator is the best linear unbiased estimator. You know what blue means, right? But the ordinary least squares estimator will only be the best linear unbiased estimator only if these assumptions hold. If some or at least one of these assumptions is violated, then ordinary least squares estimator is no longer blue. You get the idea? Okay. And you can explain what these words mean. Best. What does best mean? Best means it is efficient. It means in the class of all linear unbiased estimators, it has the minimum variance. You know, these kind of things. I'm not getting into that anyway. So that is why we have these assumptions. These assumptions have to hold in order for ordinary least squares technique to be the best, the estimator to be the best linear unbiased estimator. Okay. If you have that idea, then we should now look at the assumptions. You have seen the assumptions. There are 10, 11 of them. But now you saw them before the midterm. After the midterm, now you are going to take 4 of them and see in detail, but I'm not so sure you will do it because I don't know when you can do it. There's no time. But actually, 4 important assumptions: multicollinearity, normality, heteroskedasticity, and autocorrelation. There are other assumptions like linearity and whatever you have seen, but these 4 assumptions, we have to see them in detail, right? Now, this multicollinearity, this assumption relates to the regressors, that is the independent variables. But these other 3 assumptions relate to the residuals.
The what?
Residuals, error term, U term, disturbance term, anyhow you can call it. So what is multicollinearity? What is the multicollinearity assumption? That's what we will do today. These other 3 we can do it if we find time. But with the multicollinearity assumption, okay, assume we have, let's say we have this model, GDP equals constant plus beta 1 financial development plus beta 2 trade openness plus beta 3, what should I use? Gross fixed capital formation. Okay, assume this is our multiple regression model. We have our dependent variable GDP, and then financial development, trade openness, and gross fixed capital formation are our independent variables, regressors, right? You know the independent variables are the regressors. Now, with multicollinearity assumption, we don't want any of these independent variables to have a powerful linear relationship. That is, there should be no strong relationship between any of the independent variables. I'm insisting, independent variables. It has nothing to do with the dependent variable. You know how we can check linear relationship, right? Just check correlation metrics, and you check correlation coefficients. It tells you if the relationship is weak or strong or medium. And as I can remember, I told you that with the correlation metrics, if the correlation coefficient is below 30, it is weak. If it is between 30 and 70, it is medium. If it's above 70, it is strong, right? But with multicollinearity, we don't use 70 as the benchmark because 70 is not quite strong. With multicollinearity, we have a higher benchmark because these independent variables have to really be powerful. The relationship between them has to really be powerful before we can say there is multicollinearity. So in some books, or other people have other ideas. For instance, if you read the Gujarati textbook, they will tell you the benchmark is 80%. So if you see correlation coefficient above 80, you should consider that there is multicollinearity. But other professors have their own ideas. Like for instance, Kohan Hoja says he considers 85%. Nigar Hoja says she considers 90%. That's why it's good to use more than one test, because with this correlation metrics, at times you can see 85%, 90%. You might feel like there's multicollinearity, but meanwhile there is no multicollinearity. Or maybe you might see 80, you feel that there is no multi. So it's good to use a different test at least to confirm your results. I'll show you all those tests, but I'm just giving you an idea that none of the independent variables should have a powerful linear relationship. Ask me, I'm more cautious. So is somebody at the door you can open? For me, I am more cautious, so I consider 80% as the benchmark. So whenever I see correlation coefficient 80% and above, I am suspicious of multicollinearity. So I try to check the other things to see if there is multicollinearity or not. Okay, if you have that idea about multicollinearity, then I can tell you how to detect multicollinearity. First of all, if you run a regression or if you have your data on eViews, before you can formally check for multicollinearity, you can have some hints. You can look at the results. If you have a high R squared, but most of your coefficients are insignificant, it gives you hint of multicollinearity. High R squared with most insignificant coefficients. Because if a root square is high, it means your model has a good explanatory power. So you expect your coefficients to, at least most of them, to be significant. But if you have a high root square and then instead most of your coefficients are insignificant, at least it gives you some hints that there might be multicollinearity. But that's just an informal test. It's not even a test, it just gives you some hints. But to formally test for multicollinearity, we can use the correlation matrix. And we can also use what is known as variance inflation factor. I've heard about this. Heard about it?
Yeah.
In class?
Yeah.
Variance inflation factor / tolerance factor, whatever. So we can use these two things to formally test for multicollinearity. Now, how do we make the decision? With the correlation matrix, again, it is just between the independent variables. It has nothing to do with the dependent variable. With the correlation matrix, we don't want powerful linear relationship. So if you see very high correlation coefficients like 90-something%, 98, 97, then you know that there is multicollinearity. So if you see, for me, if you see above 80, you should be suspicious of multicollinearity. So try to check variance inflation factors to confirm your results. That's why I'm telling you that some people, their own benchmark is 80, others is 85, others is 90. But for me, I'm a little bit more cautious. If I see 80, I'm suspicious that there might be multicollinearity. So I want to check variance inflation factor. Okay. I think we should do practicals on that. And then, okay, that's with correlation matrix. Let me tell you, with variance inflation factor, we don't want variance inflation factor to be more than 10. We use 10 as the benchmark. So if all of them are less than 10, then we can say there is no multicollinearity. But if at least one of them is greater than 10, then there is multicollinearity, right? And with this correlation matrix, you should not wait for all of them to be high. If just one is high, it is enough. If just one coefficient is high, like more than 80, then we have multicollinearity. Okay. And with variance inflation factor, if just one of it is more than 10, we have multicollinearity. Okay. I have data here. I will show you practical so you should understand better. 1987 to 2019. To 2019. What's the data? GDP, total stocks, GDP, total stocks, trade, gross fix, so trade output CRO, gross fixed capital formation. Stocks traded, market cap, so I'll put ST, then MC. ST, MC. Oh my God. Okay. Guys, I'm not feeling too well today, so I'm facing some kind of difficulties. I should paste my data here. Okay, we have our data on e-views, right? So now we want to check if, by the way, GDP is dependent variable, and then we have 1, 2, 3, we have 5 independent variables. TS, TRO, GFC, ST, whatever, 5 independent variables. So remember, with multicollinearity, we don't want any of our independent variables to have a powerful linear relationship. So we are not interested in GDP. Multicollinearity has nothing to do with dependent variable. It is only independent variables. Be careful. So I will show you two things. First, what we did before the midterm, I showed you how to check correlation metrics. So I will take all the variables, including GDP, because I want to highlight that GDP is good to start. What's CS, CRO, it's gross fix, STMC. So these are our variables. I'll just press enter. I come here to view covariance analysis. I should change this covariance to correlation, and I get my correlation metrics. You know this, right? Okay. Now, looking at the correlation metrics, what do we notice? For instance, you notice this 0.17 is the correlation coefficient between GDP and TS, right? This 0.33 is the coefficient between TRO and ST, right? Now, look at all these correlation coefficients here. Forget about GDP. The dependent variable has nothing to do with multicollinearity. We are interested only in the relationship between the independent variables. So look at all of them. None of them is up to 80, I think. This one is 71, but it includes GDP. It's for GDP, it's not our concern. So none of them is up to 80. So based on this, we can say there is no multicollinearity, because if you have at least one of them which is like above 80, really powerful, then it means there is multicollinearity. You get the idea? Now, in order for, at times, which one is one? No. It is with itself. All this, where you see ones, it's variable with itself. A variable is perfectly correlated with itself, right? Okay. I think here is 62. It's not powerful. 68. So here is 71. It's not powerful. So we can say there is no multicollinearity based on these results. Now, there is a way you can get these correlation metrics without including the GDP, without including dependent variable. You know, for multicollinearity, we don't care about dependent variable. So this way I've showed you is the way I showed you before. So let me show you now a way you can get the correlation metrics without including dependent variable, because we don't need dependent variable for multicollinearity. Oh, what am I doing? Almost closed. So what you can do is come to quick, come to group statistics, correlations. Have you seen? And then just write the variables here. Sorry? Yes, there are many ways you can do it. You are right. Yes, so just type out the variables here, the variables you want to check correlation coefficients for, excluding dependent variable. For instance, I'll just type TS, TRO, gross fixed capital formation, ST, MC. That's all. I don't include GDP. And if I press enter, I get correlation metrics only for the regressors. Then you can interpret your results. Okay, no correlation coefficient is above 80%, therefore there is no multicollinearity. But if you find at least one of them which is above 80, it means there is multicollinearity. Again, like I told you, it's good to perform more than one test to confirm your results. So we should also check variance inflation factor. Now, if you want to check variance inflation factor, you must run a regression. You see, to check correlation metrics, we have not done any regression. But to check variance inflation factor, we must do a regression before we can check variance inflation factor. So let's do a regression. Quick estimate. You know, with regression, GDP is dependent variable, right? Constant. Next, CS, CRO, gross fixed capital formation, STMC. I run my regression. This is my regression output, right? Now, before interpreting, okay, we have no hints of multicollinearity just by looking at this output. Remember, I told you that just by looking at your regression output, it can give you some hints of multicollinearity. For instance, if you have a very high arrow squared and most of your coefficients are insignificant, it gives you some hints. But you discover that here our arrow squared is high and all our coefficients are significant. All these prop values are less than 5. So all coefficients are significant. So based on that, we don't really have hint of multicollinearity. So how can we check variance inflation factor? Come to view, coefficient diagnostics, variance inflation factors. Have you seen? And you take enter. Now, with the variance inflation factor, at times you can get conflicting results. Like if you see this, guys, focus on the centered VIF, centered variance inflation factor. Don't bother about this uncentered variance inflation factor. If you look at this centered VIF, it is telling us that there is multicollinearity, because according to the variance inflation factor, none of them should be higher than 10, because we use 10 as benchmark. If all of them are below 10, then it means there is no multicollinearity. But if at least one is higher than 10, it means there is multicollinearity. You see, we have 17 here, so it's telling us that there is multicollinearity, you understand? So the results we got from correlation metrics is conflicting with the one we have gotten from variance inflation factor. This is a special case because this data, I just downloaded it arbitrarily. But typically, if you are working on a study and you download data neatly, then most of the times the results you get from the correlation metrics will be the same as the results you get from the variance inflation factor. If correlation matrix is telling you that there's no multicollinearity, then if you check variance inflation factor, you will not see any of them which is more than 10. You understand?
I'm sorry, no, because you're talking really fast.
Because I'm recording, so you can watch it. I'm talking fast.
No, because you're talking really fast. Even in the video, sometimes I have trouble to understand what you're saying.
No, but you should pause, listen, pause, write, listen. That's what I do in my courses. If I'm watching videos, if they record, I have my microphone, I listen, I pause, I write, I come again, I play, I listen. So just to watch 1 hour video can take me like 5 hours. Do you understand? I have just 1 hour. There's many things I want to do. If I talk slowly, I will not do anything. So you want me to say, okay, this is 17, there is no variance. Is that why you want me to start talking?
Keep going like that.
I know I'm fast, but I know I'm recording. So if you don't understand, you can watch the video. And it's because I have limited time. Understood? Okay. By the way, I hope you don't take your dog to Iran. I hope you won't take your dog to Iran. Because they will kill your dog. Better bring it to us, so we know what to do with, we know what to do with it. Okay, guys, you get the whole idea, right? So with multicollinearity, we have 2 tests. We check. What do we check? Correlation metrics, and we also check variance inflation factors. With the correlation metrics, we are concerned only with the regressors, independent variables. It has nothing to do with the dependent variable. We don't want the correlation coefficient for any of the regressors to be quite powerful. It should not be like higher than 80%. With variance inflation factor, we don't want any of the centered variance inflation factors to be more than 10. Like 10 is the benchmark. You understand? So if any of the VIF is above 10, it means we have multicollinearity. For correlation metrics, if any of the correlation coefficients is higher than maybe 80-85%, we can say we have multicollinearity. Again, multicollinearity is only for the regressors. It has nothing to do with the regressor or dependent variable. Okay, that is it for multicollinearity tests. Now, let's assume that we have found multicollinearity. We are trying to carry out a study, and in our model, we have found multicollinearity. How can we solve it? Guys, I think I should mention something about tolerance factor. On E-views, you cannot get tolerance factor. You can only get variance inflation factor. The tolerance factor is the reciprocal of variance inflation factor. You're correct. So variance inflation factor is equals to 1 over tolerance factor. Or you can say tolerance factor is equals to 1 over variance inflation factor. It means 1 is the reciprocal of the other. So if you get the variance inflation factor from E-views, just take 1 divided by that factor, it will give you the tolerance factor if you want to calculate it, right? And what's the decision? With variance inflation factor, we don't want high variance inflation factors. It should not be high. It should not be more than 10. If it is more than 10, then there is multicollinearity. With tolerance factor, it is the reverse. We don't want tolerance factors which are very low, close to 0. If it is really low, really close to 0, then there is multicollinearity, because 1 is the reciprocal of the other. So we don't want high variance inflation factors, and we don't want low tolerance factors. But for me, no need to report both. If you report variance inflation factor, it's fine, because tolerance is the reciprocal of VIF. So if you report VIF, it means you are indirectly reporting tolerance. You get the idea? And you cannot find tolerance on E-views. You can find just VIF. Okay. If that is understood, then solutions. Now, assuming that we have our model and we have found multicollinearity, guys, this is our model. Dependent variable is GDP, and then we have 5 independent variables, right? So let's assume that we have found multicollinearity. Let's say, looking at the correlation coefficients, let's say the correlation coefficient between ST and MC is like 90%. So it means these are the 2 variables that have caused us to have multicollinearity. So in order to solve it, we can remove one of the variables. So let's say these 2 variables have a higher correlation and the other variables have a good correlation, which is low. So these are the 2 variables that have caused us to have multicollinearity. So in order for us to eliminate that multicollinearity, we can remove one of the variables. So we can remove either ST or MC. But then, that's the first solution. But then you don't just remove variables anyhow. You need to be careful. There are some variables which are very important and they need to be in the model. So if you remove that variable, then you create a problem. So by trying to solve this multicollinearity problem, you create another problem. And this other problem you create is what we call omitted variable bias. Your results will be biased. Why? Because an important variable has to be in your model, but you have removed it. You get the point? So you don't just remove variables anyhow. If you feel like removing a particular variable, or let's say all the variables in your model are really useful and you cannot remove any of them, then you can use different proxies. You can use different proxies. For instance, if one of the variables in your model is financial development, you know, for financial development, there are many proxies you can use. You can use financial development index. You can also use domestic credit to private sector. You can use market capitalization. I mean, there are many measures you can use to measure just financial development, many proxies. So if you're using a particular proxy and it is causing multicollinearity, then try a different proxy. You understand? Just because you cannot take off the variable totally. But if taking off the variable will not cause omitted variable bias, then take it off. Now, how will you know that this variable will cause omitted variable bias? You don't guess. You should test it. There is a test for that. So whenever you, yes? Sorry? Yes, whenever you use a different proxy, go back again and test for multicollinearity. Test again to see if you have solved the problem. You understand? Because maybe you might change the proxy and there is still multicollinearity. So whenever you change the variable, you use a different proxy, or you eliminate a variable, retest again to check if multicollinearity has been solved. If it has been solved, fine. If it has not been solved, then use another method. Okay, so I'll tell you how to test for omitted variable bias, but before doing that, let me tell you the other possible ways you can solve multicollinearity. So one of them is you can eliminate one of the problematic variables. You can use a different proxy. You can use log transformation. Let's say maybe you're using levels data. Try to get a logarithm. Maybe it might help. You can use log transformation, and you can also use ratio transformation. What do I mean by ratio transformation? Like you can combine variables. Let's assume two of the problematic variables are, let's say, GDP and population. Let's assume in your model, sorry? Yes, but GDP is dependent, okay. Because what I was saying has nothing to do with, okay, let's use income if your problem is GDP. Let's assume that these two independent variables are in our model, and these are the problematic variables. These are the variables which have multicollinearity, which are causing multicollinearity. So if we have tried all these methods and it has not worked, and we don't want to exclude one of these variables, then we can do ratio transformation. We can combine the variables. So what you can do is you can combine these two variables into one variable. You can take the income divided by the population, and it will form a new variable known as income per capita, right? So whenever you see per capita, it simply means it has been divided by population. So if you see GDP per capita, it means GDP divided by population. So you discover that if you are using now income per capita, this single variable is accounting for these two variables. So we have combined both of them. So we can do this kind of things. You get the whole idea. So, but first of all, if you find multicollinearity, identify the problematic variables, the variables which have this high correlation. Try to change the proxy. Try to use a different proxy. If it solves the problem, fine. If it does not solve the problem, try to eliminate one of them. But remember, whenever you eliminate a variable, you might cause a different problem, which is omitted variable bias. So you need to check if this problem has been caused, and I'll show you how to do it. If it does not work, you can use log transformation. By the way, guys, always work with log, because just by taking logarithm, it solves so many problems in your data. So right from the beginning, it's always good to get the logarithm before you start doing anything. If it does not work, you can try ratio transformation. This kind of solutions, most probably you might find solution. Okay, I will show you now how to test for omitted variable bias. Let's assume you remove a variable and you want to test if by removing that variable, you will create omitted variable bias. Okay, let's go to eViews. So again, this is our model, right? So let's assume we want to remove this last variable, MC. So we'll run the regression without the MC. So I will run my regression. Why is it not? GDP constant TS TRO gross fixed capital formation ST. So I'm not including MC, right? That is, I'm assuming that these are the two problematic variables. These last two, ST and MC, both of them have high correlation. They are causing multicollinearity. So I want to remove one of them. I remove MC. Okay. Guys, before you remove a variable, I will run this regression with MC. I'll show you something. MC. So I'll run the regression with all the variables. This is my regression. Now let's assume that these two variables, ST and MC, are the problematic variables. So I want to decide which of them to remove. You don't just pick any one. Run the regression with all the variables. Come and check their significance. The one which is least significant, remove it. So between ST and MC, unfortunately for us, all of them have 0, 0. But sorry? No. CRO? No. I'm assuming that it is these two variables which are the problematic variables. So you cannot come and remove TRO because TRO is not causing multicollinearity.
No, maybe it's for significant test studies.
Okay, I get. So if you find a problem, how will you know which of them is problematic variable? You check correlation metrics, right? The variables which have this high coefficient, which have this high correlation coefficient, those are the variables which are causing multicollinearity. So you want to remove one of them. So I'm assuming that it is ST and MC which are these problematic variables which are causing multicollinearity. So I want to remove one of them. I will run the regression with all of the variables. Then between these two variables which are my problematic variables, I will check which of them is least significant. You understand? Which of them has the lowest significance? If any of them is insignificant, remove that one. But if all of them are significant, which one is more significant than the other? Maybe this one is significant at 5%, this one is significant at 10%. You know, 5% is higher than 10% and 1% is the highest. So the one which is more significant, keep it. The one which is least significant, remove it. You get the idea? Okay. If you have gotten the idea, so again, let's assume that I have checked the significance and MC is the least significant. So I want to remove MC. I will run the regression now without MC because I want to remove it. GDP constant, TS, TRO, gross fixed capital formation, ST. I will not include MC because I want to remove it. So I run this regression. Now this is my regression. Okay, if I run this regression, again, first of all, I have removed MC, right? Because my initial model had multicollinearity, I'm assuming. So I'm removing MC because I'm trying to solve this problem. So I should check now if this problem has been solved, right? So if you run the new regression, you should go now and still check variance inflation factors, right? Check whatever, but I'm not checking. I'm just showing you what to do. Oh my God. So if you remove the variable, go back and check variance inflation factors, still check correlation metrics to see if this problem has been solved. If the problem has not yet been solved, try another solution. But if the problem is solved, let's assume that we have removed MC and the problem is solved. But now, by removing MC, we might have created another problem, which is omitted variable bias. So we should check now if we have created this new problem or not. Okay. So I keep doing this thing. So this is the regression, TRO, gross fixed. Oh, thank you. ST, constant. Guys, the constant can be at the end, beginning, it doesn't matter. So this is the regression now without MC. Now I want to check if I have committed omitted variable bias or not, right? I should come to view. I have my regression results without MC. I should come to view. I should come to coefficient diagnostics, omitted variables test. Have you seen? Omitted variables test. Click it. And then now, I should write something here. What should I write? I should write the variable that I have removed, because I'm trying to see if that variable is important or not. So the variable that I've removed is MC, right? And I click, if I write MC, I click OK. Now this is the test results. I will show you the hypothesis. By the way, I think it's written there. Okay, it's written here, you don't even need to cram it. This is the null hypothesis. The null hypothesis says that this MC variable is significant. That's the null hypothesis. The null, okay, it is not significant, correct? So Now, what I will check is probability values. I can check probability values of the F statistic. This probability value is less than 5%, right? Which means I will reject this null. Let me write it because you might be missing it. What's the null hypothesis? MC is insignificant. Therefore, what would the alternative hypothesis? MC is significant, right?
Yeah.
Okay. If I have these results, I should check F statistic, probability value. You can check C or F since it is just one variable we have omitted. But if you omit more than one variable, check F. So to be on the safe side, always check F. Forget about C. Check the probability of F statistic. It is less than 5%, which means that at 5% level of significance, we can reject this null hypothesis and accept the alternative. What is the alternative? It tells us that that variable is significant, which means we were not supposed to remove it. Therefore, there is omitted variable bias. So we should go back and put the variable, because if you remove this variable, then you have created omitted variable bias. But if we are not able to reject the null, it means this variable is not significant, so we should remove it anyway. It doesn't create any omitted variable bias. You get the point? So in this case now, it has showed us that, okay, fine, we have removed this variable, it has solved multicollinearity problem, but it has created a different problem. So we should go back and put the variable, and then we should look for a different way to solve multicollinearity. So if we go back and put the variable, remember initially the two problematic variables were ST and MC, right? So we have removed MC, we have solved multicollinearity, but we have created omitted variable bias. So put back the MC and then now try to remove ST and repeat the process. Maybe it might solve the multicollinearity without creating omitted variable bias. If it is not possible, try other solutions, as I've told you. Maybe change the proxy, or maybe use log transformation, ratio transformation, whatever. But at least you get the idea, right? Okay. We have 2 more minutes, but we have 7 more minutes. You understand? Who has not understood? We have 2 more minutes, but we have 7 more minutes.
You want to ask to send
25.
225. 225. As usual. So instead of 220, we'll do 225. Actually, I'm done, but I just want to keep you here because
Yeah, next week is the last week, that's why.
okay. Guys, have you understood everything about multicollinearity?
Yeah.
We don't want a powerful linear relationship between our independent variables. To check for it, run the regression first, look at the R squared, look at the coefficients. If you have a high R squared, but most of your coefficients are insignificant, it gives you some hints that there might be multicollinearity. But to formally check for multicollinearity, use correlation metrics, use variance inflation factor. For correlation metrics, we don't want powerful correlation coefficients. It is just between the regressors. It has nothing to do with the dependent variable. Okay. For variance inflation factor, we don't want higher variance inflation factors. It should not be more than 10. You know, variance inflation factor is the reciprocal of tolerance factor. So we can use the variance inflation factors to calculate the tolerance factor. And in order for us not to have multicollinearity, we should not have tolerance which is close to 0. If we do all of that and we detect multicollinearity, then there are various ways we can solve it. We can remove some of the variables which are problematic. We can change the proxies. We can use log transformation. We can combine the variables, whatever. But know that if you're removing a variable in order to solve multicollinearity, you might create a different problem, which is omitted variable bias. So whenever you remove a variable, then you have to check if you have created omitted variable bias or not. And whenever you try to solve multicollinearity by using any method, after, let's say you change the proxy, or maybe you use a different, you remove one of the variables, always test again to see if actually this problem has been solved or not. You get the whole idea. Okay, you want to say something?
Yeah, Dr. Miguel also mentioned to check if there is bias or not. We need to check,
Function.
after we omit the variable, we need to check the adjusted R squared and make a comparison between R squared and adjusted R squared. If the R squared is high, but the adjusted R squared is low, it means that creates the bias.
Yes, that's a hint as well. You know, like I told you, we don't want a difference between R squared and adjusted R squared. If there is a gap between them, it means some of our regressors have problems. Some of them are useless. You understand? And this problem might be caused by maybe we have included useless variables, or maybe there is multicollinearity. So it's a hint. It's a hint. But actually, if you check the R squared, check the coefficients, check the adjusted R squared, these kind of things just give you hints if we have multicollinearity or not. But to formally test for multicollinearity, it is correlation matrix and variance inflation factor. Actually, there is a third method, auxiliary regressions. I cannot show you that because I don't have time.
Actually, didn't explain that one.
I don't have time to show you that. We can also check multicollinearity using auxiliary regressions. Just put it in your mind. But I have no time to show you that. Correlation matrix and variance inflation factor is enough. It will tell you if there is multicollinearity or not. I think that is fine.
We are earlier for 3 minutes and then for 2 minutes.
We have 3 more minutes. You should not be in a haste. So, guys, whenever we meet again, we'll look at heteroscedasticity, autocorrelation, normality. You have already seen normality when we're looking at descriptive statistics. We saw Jack-Barrett test, right? Because it is the same Jack-Barrett test we are going to use to check normality. But the normality you have seen is normality of the data. But this time around, we want to check normality of the residuals. Because you remember these 3 tests, autocorrelation, heteroscedasticity, normality, these are residual diagnostics. They have to do with the error terms, residuals. So we'll check that most probably next week. Then, if I don't forget, if I forget, remind me. I'll also show you how to check functional form and.
Why did we do that for error term?
For error term, residuals.
Why we need to check normality and heteroscedasticity and that is.
Okay, you mean why we're checking about the error terms? Actually, intuitively, what I can think of is because you know error term is the unexplained part. In your model, you have the explained part, which are your variables and the coefficients, and the error term is the unexplained part. So at least for the explained part, we know about it. We have data. For the error term, we don't know anything about it. So we want to make sure everything is fine. That's just what I'm thinking. I'm not so sure I'm too correct, but intuitively, that's what I can think. But these assumptions, most